in spite of the very difficult situation outside. And thanks very much to SRT Bhopal for this very warm invitation. And this is probably the first talk that I'm giving since I took over as ACM president a few days ago. And we hope that you might find this particular presentation of some interest, especially to the graduate students in this audience here. Okay, so the background to this whole exercise is that, as you might have noticed, there is a common perception in the general public at large, and certainly in our popular media, that breakthrough ideas are predicated on spectacular new concepts, which, when you hear of them for the very first time itself, convince you of their brilliance. So, for example, something like quantum mechanics. But if you are a budding researcher and you are worried about, and just like me, and I am also in the same situation, about your ability to come up with such game-changing ideas, then the message of this particular talk is that don't worry, because often you can come up with equally potent results, even with absurd, or to put it more bluntly, stupid ideas. The key here is that it is not enough to have one stupid idea, because then you will not get very far. So what you need is at least two stupid ideas, and if you are really good at it, many more. And what you might find is that although individually they don't make any sense, collectively they surprisingly may work well either in tandem or in groups and come up with extremely surprising and innovative contributions that are welcomed by the rest of the community. And as a proof of example of this particular thesis, I will use the metaphor of robust query processing in this particular talk. So before I get into the actual technical presentation itself, I thought that it might be nice for you to get an intuition as to the kind of thesis that I'm propagating here. And I thought I could convey that well to you by giving you an example from the real life. So I'm moving to the second slide. And what you will see here is that this slide refers to the expense estimates of the Commonwealth Games in 2010, which all of you would remember was held in Delhi. And there was a lot of press and media about the organization of the games. And especially there was about the amount of money that was spent on the entire games. So if you look at the newspapers and at that time, they all said that the government notifications that were issued, you would see that the government valued the entire expense to be something of the order of around 5,000 crores. But when you as a Aam Aadmi see this number, you realize that this is way too small. Obviously, it can't be as small as 5,000 crores. So this number is probably not of much use. On the other hand, if you had asked our hyperventilating media at that particular time, you would see that there are numbers like 70,000 crores that were being bandied about, especially in the 24-hour TV channels. And they said this is an enormous amount for a poor country to be spending on the Commonwealth Games and so on. Now, again, 70,000 crores seems a very large number to wrap your heads around, although in light of subsequent events, maybe even this is small. But in 2010, a number like 70,000 crores essentially looked like infinity. And it looked impossible for so much money to have been spent without people noticing that something was wrong. So what you would say here is that you have two numbers. One is the 5,000 crores, which looks like a gross underestimate. On the other side, you have the 70,000 crores, which looks like a extremely large overestimate. And you might say both these numbers are useless. Let's just drop them in the waste paper basket and move on with that. But in spite of the fact that individually these numbers don't make sense, if you happen to take the geometric mean of these two numbers, that is of 5,000 and 70,000, then the number you'll come up with is something like 18,700 crores. And believe it or not, if you go and look at the CAG report, that is the Comptroller and Auditor General's report, which was authorized by Parliament to go and investigate the actual expenses of this particular games, you'll find that the number is surprisingly close, which is around 18,500 crores. Okay, so the point I'm trying to make is that even though you started off with extremely silly numbers, you could still come up with something very meaningful by combining them in the right way. You will also notice this when you go and do haggling in any of the street markets. Usually the person selling it to you will say some amount like X, and then you, which is a fairly large amount, you will say something like Y, which is much smaller. then they will say X by 2, and you will say 2 times Y, and so on. And you keep going like this, where the vendor is decreasing the amount and you are increasing the amount until you reach a consensus. Next time, just ask them to take the geometric mean of their number and your number, and you'll come up with the correct price. Okay, so with this background, I'll move on now to the technical part of this presentation, which deals with robust query processing in database management systems. Since I was told that there is a heterogeneous audience of students and faculty in this today on this online presentation, I thought I'll give you the world's quickest overview of database systems, which will also set the stage for the specific technical contributions that I would like to talk about in the remainder of the presentation. So database management systems, or DBMS as they are more affectionately known, are these extremely large and complex software systems. They run into not thousands or tens of thousands, but millions of lines of code. And it is intended for efficiently and conveniently handling data. And this is enterprise data that we're talking about here, not your home information, but large enterprises like the Reliance or the universities or the government and so on. And you want to be able to handle data through its entire life cycle, starting from capturing the data, then subsequently storing it, asking questions of this data, and maintaining them for the long term. Not surprisingly, you will find that database systems are the cornerstone of our software industry today, which is very popular in India. And you find that the majority of the computational infrastructure, the majority of the intellectual infrastructure, and the majority of the financial infrastructure is being used by database systems. You'll see the numbers that are showing up here. We'll see that more than 80% of the computers are used for database related applications. More than 70% of the people working in the software industry do something or the other related to databases. And finally, it is the largest monetary sector of the computer business. So and some of the well-known current database systems which you might relate to are for example, you have commercial database systems like DB2, which comes from IBM, and then you have SQL Server or SQL Server, as it's also called, from Microsoft. Then Hewlett-Packard or HP has a very large parallel database engine called SQL-MX. Then Oracle, which is very popular in India, has a software offering called Exadata. And then there is HANA, which forms the base for SAP's current ERP offerings, and so on. There are also several public domain software which are completely free, like PostgreSQL, which has been used by many startup companies to jumpstart their initial prototype systems. Then there is also MySQL as well as Berkeley DB. And the reason that all these various database engines have become extremely popular is that they come armed with a large number of goodies. And in particular, I just talk about two of them in this presentation. The first is that database systems offer you peace of mind. And what I mean by that is that any changes that you make to a database a repository are guaranteed to be immune to any kinds of subsequent failures, whether it's a power failure or whether there's a hardware failure or something else goes wrong. All the changes that you made to the database system or the repository that you have within your organization are guaranteed to be immune to such failures. So in a sense, you can think of them as the Sri Ravi Shankar of the information world. Minus the long hair, of course, because database systems are much more sober. Okay, so this is the first point. The second reason that database systems are extremely popular is that they support what is called as declarative access. Here, if you have a particular objective, you only state the objective, but not the process to reach this objective. That is, you state what you want, but not how to get it. So this is very different from the standard programming that most of your students would be used to, which is called as imperative programming, where you have a particular goal and then you specify every step of the way. So for example, if you wanted to invert a matrix, then you would say, okay, first put the matrix into this array, and then these are the steps that you need to do, and finally out comes the inverted matrix. But in databases, it's very different. You just say, I want to invert the matrix, and then the system itself figures out how it should do this inversion process. Okay? So in this sense, it is very similar to what professors do to PhD students, at least in IISc. When they ask them, when the poor student comes and asks you, okay, well, what should I do for my research thesis, all that we say is go write a great thesis. Don't ask me how. Of course, I'm sure in SIRT Bhopal, the faculty are very nice. They write the thesis for you. But in many other places, people usually say that you have to go and figure this out yourself. So this is what is meant by declarative access, is that unlike imperative programming, you specify only the ends, but not the means. And this is what I'll focus on for the rest of this talk. So in the database world, what has become very popular, and all the previous examples that I showed you are all fall into this category, are what are called as relational database systems, or RDBMS. And these are all based on this mathematical foundation of first order logic. And this was designed by Edgar Codd of IBM's Almaden Research Center, for which he received the Turing Award, which, as you might know, is equivalent to the Nobel Prize in Computer Science. And he received this in 1981. So in the database community, we have this nice saying we believe in Codd and not God. And the basic idea that Codd had was that, unlike the previous database modeling frameworks that have been developed in the 1950s and 60s, where there was things like the network model, hierarchical model, and so on, where much of the connections between information was hardwired. Here, instead, he said that all data should be stored in a set of relations. So this is the mathematical notion of relation, which for the purpose of this talk, you can think of it as essentially tables. So you have a table with rows and columns. And these columns are called as attributes. And then there are relationships between the tables, and there are various kinds of constraints that operate on these attributes and tables. To give you a very simple example, here's a simple university database, which has 3 tables. There's a student table, which has the roll number, the name, and the address. And then there is a course table, which tells you the number of the course, what is the title, and how many credits you get if you join the course. And finally, there is a register table, which combines the information in these 2 tables, that is the roll number of the student and the course number, and tells you which student has registered for which course, as well as the performance of the student in that particular course. Okay. So this is the schematic information of the tables. This tells you the name of the tables and the column headers. And then you can add information in each of the rows. Okay. So for example, here you will find that Jayant in Bangalore has a roll number of 81061. This was actually my undergraduate roll number, so you can figure out how old I am from this. And then I have registered for the database management system course, DBMS, called E0261, which is actually the number in IISc, which is a 4-credit course. And since I made up the slide, I was very kind to myself. I gave myself an A+ in this particular course. Okay. So this is the way that we represent information in the database. And one of the constraints that you see here is that some of the attributes have underlines under them. Underline basically means that all the values in this particular column will be unique, that there will be no repetition. So things like a roll number or a course number are obviously going to be unique. Just to check, am I audible clearly to the audience? Is there anything that we need to change, or shall I just continue? Professor Shukla? Hello, Professor Shukla?
Yeah, we can continue, sir. We can continue.
Shall I continue? Okay,
yeah. I'm handling the chat box. If anything comes, then I will.
Okay, sure. I just wanted to confirm that I was not speaking to a blank wall. Okay, just do that. Yeah, so now if you look at the way that we interface with database systems, there is something called the structured query language, or SQL or SQL, depending on how you want to pronounce it. And this was again invented, like most of the well-known database technologies were all invented by the IBM company in the early 70s, specifically the Almaden Research Center, which is in the located in California. And to show you an example of this language in operation, suppose on the database that we had, which is the university database with information about students, courses, and which students have registered for which course. Let's say the Vice Chancellor wants to, or Professor Shukla would like to list the names of the students in the courses. That is, we don't want to know the roll number or course number. I want to have the name of the student and the course title. That is, that Jayant has taken the database course. So for this, you would write a query, which is what you see in the central box here. The green words like select, from, where, and so on, these are keywords for the language. And then you see information inside, which is in red. And what the first line is saying is, select the name of the student, that is what you're interested in, as well as the title of the course. So this is what you want to be output. Now, where should this information be taken from? It should be taken from 3 tables that is the student table, the course table, and the register table, or equivalent relations. And how do you make sense of the combination of information across these tables? You need to equate the roll number of the student with the roll number in the register table. Similarly, you need to equate the course number from the course table with the course number from the register table. This is how you do the linkages between the various tables and produce the output. So if you look at this description, you'll see that, as I mentioned earlier, that SQL is not an imperative programming language, but a declarative language. That is, it only specifies the target, but not the means to achieve the target. So you might be wondering what was left unspecified in this particular query or SQL query that you had written to output the names of the students and the titles of the courses. So firstly, when I need to combine information across tables like the student and the register table or the register and the course tables, this is usually called as a join in the database terminology. That is, you're joining the information in a pair of tables. Now, if you look at the order in which these joins are implemented, it's a binary operator. It takes in two tables and produces another table as the output. One option that you have is to join the student and the register table first. This is what you see in this join order line. So you could join S with R, and that bow tie symbol that you see, which is essentially the double cross, that is the join symbol in the database algebra. So you can join a student with register first and then join it with course. That's what the first brackets show you. S join R and then join with C. Or maybe for Vastu reasons, you might decide to join R with C first and then with S. The output of both these different sequences or permutations would be exactly the same. Reason being that join is both an associative as well as a commutative operator. So you can easily prove that any such sequence will produce the same result. Yeah, but the difference is that the amount of time taken to produce the result could be drastically different. The first sequence may finish in a few seconds. The second sequence may take you a few years to complete. Ultimately, they'll produce exactly the same answer, but the time taken to produce answer could be very different based on which sequence you actually chose in executing this particular query. Now, even if you have decided the sequence that it should be, let's say, a register joined with course first and then joined with the student table, for this logical operator called the join, there are many physical implementations that have been proposed in the literature. So especially in the 70s and the 80s, it was the cottage industry to come up with new ways of implementing the logical join operator. And there are well-known techniques like nested loops, which is essentially two for loops with pointers moving across the two tables. Or there is something called sort merge, then there's hash join, there's index join, there is semi-join and so on. So there's a wide variety of techniques that are available. So even if you decide the sequence, you still have to decide the mapping from the logical join operator to the physical answer. And this is supposed to identify the optimal strategy for executing your query. So for the purpose of this talk, we will use this word as called plan, which is what is commonly used in the database community, that is for defining the optimal strategy. So the query execution plan, or plan for short, tells you what is the best way of executing this query in order to achieve the desired objective. So if in case you have never seen this strange animal called a plan before, here is a specific example which is connected to the earlier SQL query that we showed you, where we were trying to output the names and of the students and the courses they were taking. This tree that you see in front of you is evaluated bottom up and has the basic tables like student, course, and register at the bottom. And as you go up through the tree of operators, various kinds of computations are being done on the data. And at the very top, you finally get the output. The output contains the names and the courses. So what this particular tree of operators is doing is to tell you, for example, that if you look at the course table, which is in the middle, use an index scan to access the information. Typically, the indexes, if you remember your undergraduate database course, is something like a B+3 would be used here. So you use an index scan to access the rows in the course table. And then you are supposed to join this with the register table, for which a sequential scan has been issued earlier. So that's called as a table scan, where you scan it from one end to the other. And then after the sorting of that particular information, you can combine this with what is called as a sort merge join. And then the next layer is the hash join, where you're combining the information with the student table. So you first join course with register using a sort merge join, and then you did a hash join with the student table in order to finally output the desired results. You'll also see that each of these operators that you see here has two annotations. There is a green annotation and a red annotation. The green annotation basically tells you about the amount of data that are measured in number of rows that is flowing from one operator to the next downstream in this tree. So for example, if you look at the bottom left operator of table scan, you'll see that it says card is 1000. So what it means is that the number of rows that are output by this operator, which are then sent to the hash join, which is the next operator in the tree, is 1000. So this is telling you the volume of data that is flowing from one operator to the next in this tree. And then, so just saying there was some, okay, there was a question or so. Somebody raised a hand.
No, sir. I have requested for the question. If anybody want to ask any question, he can post, he or she can post on the chat box.
Okay, so fine. But anytime you want me to stop, please let me know.
Yes, sir. Yes, sure.
Yeah, so then the second number is the red number that you see, which is called as cost, which tells you the amount of effort that is involved, usually measured in terms of time, in order to process the data that has come to this operator. So again, for this table scan operator just above the student table, you'll see that the cost is written as close to 6,800 or so. So it's just telling you what is the estimated amount of effort that it takes in order to go through all the rows in the student table. And as you go up the tree, the cost is an accumulated cost of the entire subtree below it. So if you go up to the next hash join level, you see that the cost has now increased to around 286,000. So this tells you that in order to execute all the operators in the subtree below hash join, this is the amount of effort that is expected to be required. And then finally out comes the answer. So again, even if you did not understand all the technical details here, it doesn't matter, because what we're going to talk about is something which is at a higher philosophical level. But the basic idea is that there is a query optimizer, which is saying, given the SQL query that you have input to the system, it's trying to come up with an execution plan. And the execution plan has these tree of operators, which are evaluated from bottom to the top. And in this tree, each of the operators has two numbers, which is the expense in processing the data at the operator, and B, the amount of data that is sent from this operator to the next in the tree. So now, in order to figure out how to produce this optimal plan for the given SQL query, because there is a very large exponential number of alternative choices that are available. So just as a simple motivation, if you see that there are n tables in your SQL query, there are in principle n factorial ways in which you could combine them. So you can clearly see that this is an exponential problem. In fact, it's doubly exponential in the number of tables in the query. So the way that it's done is that you give at the left input, as you can see, you give in your SQL query, you write select from where and so on, and you give it to the query optimizer. And this goes through a complex dynamic programming based exercise, evaluating many different alternatives. And then finally out comes the optimal plan, P of Q. Okay, so the input query was Q, and the output plan is the physical implementation of this query, which is P of Q, and this is expected to be the minimum cost. And for the purpose of this talk, we'll assume that the cost is essentially related to time. So essentially, when you say minimum cost, it means it's the fastest execution of this particular query, or the one with the least response time. So in order to do this dynamic programming exercise, there are two underlying models that are used by the database system. The first is to be able to estimate those red numbers, which we call as the cost. That is, how much effort does it take to process the data at each operator. And this is a function of the quality of the hardware that you have, whether it's a Pentium machine, or whether it is a supercomputer like the Cray, or do you have accelerators, or is it a CPU or a GPU or a hybrid combination, and so on. And it's also a function of how well the database engine software has been written. That is, do you have a finely tuned engine like the commercial systems, or do you have a public domain engine like Postgres or MySQL, and so on. On the right side box that you see, there is another estimation model. This is for the cardinality purpose. And this, as I said, tells you the amount of data that flows from one operator to the next in the tree. And this is a function not of the hardware, but of the database repository in terms of the distribution of data within each of the columns in the tables, as well as the correlations between the information across different columns in the database. So the distribution, the first data distribution refers to how the data is distributed within a column. That is there a uniform distribution or is it highly skewed and so on. And the correlation tells you how different columns either in the same table or across tables are related. So this is the generic practice that you would see in pretty much all the database systems. They all of course have their own secret masala, but at the core, this is the heart of the system. So now the difficulty with this whole approach is that the supposedly optimal plan choice that you came up with based on this dynamic program exercise, this was done at compile time, may at runtime actually turn out to be highly suboptimal. And when we say highly suboptimal, we don't mean that it is slower by 20%, 30%, 40%, and so on. That's perfectly fine. What we mean is that it could be, for example, 1,000 times worse. And in fact, I'll show you an example later where it is 1,000,000 times slower when the query is executed with this plan. So you thought that you were getting the ideal strategy, but in hindsight, what you will find is that the strategy you used is several orders of magnitude worse than the real ideal strategy. So you might be wondering, how on earth can this happen? Because you have done all this careful computation and analysis and identification of the ideal plan. How come you made such spectacular mistakes? So the reason for these mammoth errors is that there are errors in the models, both in the cost model, which produces those red numbers, as well as the cardinality model, which produces the green numbers. The cost model is not too bad. People have figured out reasonable ways of modeling it. So there's only a limited impact of this, mistakes that are made in this model. But with regard to the cardinality model, which tells you the amount of data flowing from one operator to the next, this can often have a huge impact. Now, there are a variety of strong technical reasons as to why there are such stupendous errors in these models. I have listed out a few of them, like core statistics, outdated metadata, attribute value independence, multiplicative error propagation, and so on. I won't go into the details here. I'll just let it suffice to say that there are important technical reasons as to why these models have such large errors in them. Now, in case you don't trust me on this, here is a proof by authority. And the picture that you see here is that of Dr. Guy Lohman, who was essentially the father of the IBM's DB2's query processing engine, a very well-respected member of the community, and who recently retired from IBM. And in April 2014, on the ACM Sigmod blog site, he had posted, made a blog post where he asked this question: is query optimization a solved problem? Okay. And the solved was in quotes to indicate the fact that he does not believe that it has been handled in a reasonable way as yet. And then within this post, he goes on to write in fairly colorful language that the root of all evil, the Achilles heel of query optimization, is the estimation of these intermediate results, which is known as cardinalities. That is, as I said, how much data flows from one operator to the next in the tree. And then he goes on to say the cardinality model can easily introduce odd errors of many orders of magnitude. Okay? As I said, in hundreds, thousands, tens of thousands, and so on. So then he ends with this very cynical statement. He says, with such errors, the wonder is not why did the optimizer pick a bad query execution plan? Rather, the wonder is why would the optimizer ever pick a decent plan? So essentially what he's saying here is the very cynical view that typically in databases, you should not be surprised if you get a bad plan. On the contrary, you should be surprised if you get a good plan. Okay? And so the point he's trying to make is that average case, the worst case is usually the average case in database systems. So since you're all familiar with this notion of best case, average case, and worst case, in most real world environments, you will find that the average case is somewhere closer to the best case side, and the worst case only occurs rarely. But in databases, it's the other way around. The average case is close to the worst case. And we'll see why this is so as we go along in this talk. But this is the very depressing environment in which we find database query optimization. And as you can see, even an industry stalwart like Dr. Guy Lohman has given this extremely pessimistic statement where he says that you have to pray very hard to get a good plan. And so most of the time, you will actually get bad execution strategies. So if you're wondering what did the database research community do on this particular problem, given its severity, there has actually been a lot of prior research on this problem. There is, this has been done over the last 4 decades or so, because this problem was identified in the 70s itself. And all this earlier research work essentially falls into 3 different streams of thought. The first is to say that let me use more sophisticated mathematical techniques to do the estimation process. So typically in current database systems, they use what are called as histograms, which are essentially piecewise linear approximations of the distribution of data. So people said that, okay, that is too crude a mechanism. Let me use stronger techniques. For example, let me use this very potent or powerful notion of wavelets in histograms. Or let me go into autonomic histograms and come in with self-tuning mechanisms. Or everybody loves machine learning today. Can I come up with some kind of deep learning based histograms using, let's say, convolutional neural networks and so on. In the line above, you see things like Sigmod 1999, VLDB 2001, and so on. What this refers to are that there are 3 main conferences in the database community, which are considered the premier conferences. One is ACM Sigmod, the other is VLDB, which stands for Very Large Databases, and the third is IEEE ICDE, where ICDE stands for International Conference on Data Engineering. So what I have written there is that there are papers on these techniques in this premier fora. Even in the last 20 years, you'll see from Sigmod 99, then 2001, 2009, and so on, there is a steady stream of activity in these approaches. The second approach is to say that instead of trying to come up with better estimation, let me try to come up with plans that are robust to the well-known errors that will definitely occur within the estimation process. And one of the well-known techniques here is called as least expected cost. This came out of Cornell University in the 90s. And again, you'll see that there's a steady stream of work starting from as early back as 1994, again in the top database conferences, and that is continuing even till today. And the third one is a very different style of approach, which is called as runtime reoptimization. And the idea here is that you initially come up with your query execution plan in the normal manner. And then as you start executing the query with this compile time execution plan, you keep comparing the results of what you got with regard to the cardinalities at each of the operators compared to what you thought you would get. And if you find that they're similar, then you just continue as before. But in case you find that there's a big discrepancy. So for example, if you had thought that there would be 10 rows coming out of the scan operator, but it actually turns out to be 10,000 rows. Or you expect that there will be 1,000,000 rows coming out of the join, but it actually turns out there is 200 rows instead. So if you find large discrepancies like this, then what you do is you go back to the drawing board and start doing a query optimization process all over again. But this time, when you do the optimization process, instead of the estimates being used for these various operator cardinalities, you actually know the exact values because you have just executed at least part of the query. So you can say, oh, I know the scan is not just giving 10 rows, it's giving 10,000 rows instead. And you can plug that into the optimization process. So replacing the estimation with the actual values and then come up with a new plan. So now you come in here and start executing this new plan. Again, you keep monitoring the actual cardinalities that you see in the operators compared to the estimated values. If you see a discrepancy again somewhere down the line, again, you do the same thing. You go back to the drawing board, but with these corrected values, you now come up with a better plan and start all over again. So that is why this is called as runtime reoptimization techniques. A lot of work has been done in this area as well. As you can see from Sigmod 1998, it has kept continuing on from there to even today. You have papers in these areas, and well-known techniques here include POP, which stands for Progressive Optimization, and REO, which is Reoptimizer. And in this context, I should say that one of the pioneering papers in this area is a person who gave the talk a few weeks ago. That is Naveen Kabra, who's currently in Pune. This was part of his PhD thesis with Dave DeWitt at the University of Wisconsin-Madison. They were essentially one of the first groups to suggest this idea of runtime reoptimization, and that is a very well-cited piece of work. Okay, so even if all this didn't make sense, hopefully you can make a better understanding of it by this cricketing analogy that I like to use. The first stream of ideas is essentially what I like to call as the VVS Lakshman technique. That is, you are extremely stylish and come up with a very good, elegant batting. So that's the sophisticated mathematics. The second is to say that we want Rahul Dravid, who's like the wall, that independent of how the wicket is, whether it's a flat wicket, whether it's bouncy wicket, whether it's spinner's wicket, you are sure that he's going to play reasonably well because his technique is very good. So this is the robust plan approach, saying in spite of errors, in spite of all kinds of problems coming in as we go along, this plan is fairly good to achieve the desired objective. And then the last reoptimization technique is probably fits in best with Mahendra Singh Dhoni, because as we all know, he's supposed to be the master of adapting to the situation, that as the IPL match or the one-dayer keeps going, based on the situation, he can change his batting strategy or the team's approach to the game dynamically and keep altering it to maximize the outcome. So this is what runtime reoptimization refers to, is to saying that as and when we run into trouble, we'll keep going and changing our policy and then coming back and using this new policy, and hopefully that will address the situation. But just like our excellent cricketers cannot guarantee anything, in the same way, although here you have several novel ideas and formulations, and as I said, Naveen Kabra himself, who gave the talk in this series a few weeks ago, was one of the pioneers in this area. They have great ideas, but none of them can give you performance guarantees. So even with all of this, you have to cross your fingers and perhaps your toes. You need to go to Tirupati and then come back and pray that your plan works well. So what we have done in our lab over the last 3 decades is that we have on this 3-decade-old problem, is that we have now come up with a completely new query processing technique. This is called as plan bouquets, and I'll cover this in the rest of the talk. And this completely abandons this idea of doing estimation. So far everybody had said, okay, the architectural box that I showed you in the beginning, where there is this dynamic programming central engine, which is based on these 2 models of estimating cardinalities and costs, that everybody had assumed, taken that for granted. And what we have done is to change the rules of the game. We said, let's throw that away completely. It doesn't work. And instead we have a new technique called plan bouquets, which abandons this process. So in this plan bouquet approach, what we do is we do a runtime discovery of all these cardinalities. We don't do any estimation at all. Instead, we discover it at runtime. And because of this new approach, for the very first time in the literature, we are now able to provide performance guarantees even in the worst case. And the performance guarantees are with regard to an offline ideal or a god that magically knows all the correct values with regard to cardinalities of all the operators in the plan. Okay? So compared to an offline omniscient oracle, we can give you performance guarantees. So for example, if there was a single error-prone cardinality estimation in the entire plan, we can give you a relative guarantee of 4. So what this means is that our plan will be no worse than 4 times the ideal plan. Now 4 may not look very impressive to you, saying you should be much closer to 1, but please remember that in general, the database slowdowns are in the orders of, as I said, of hundreds, thousands, tens of thousands, and I'll even show you the case where there's 1 million that is occurred with industrial strength database system. So in that sense, we have taken a completely terrible problem and converted it into a mildly horrible equivalent instead. Plus, even though these are the theoretical guarantees that we are giving, the empirical performance when actually measured on real systems are well within these bounds. So you'll actually get something like 2 or 3 in the normal benchmark style environments. Okay, so what I'll do in the remainder of this talk is to present to you the core ideas of plan bouquets. And in particular, I'll try to show you why this plan bouquet is actually founded on stupid ideas, but still works surprisingly well. And this is the PhD thesis work of Anshuman Dutt, who graduated in 2016 and is now a researcher with Microsoft in the Redmond campus in the US. So before I start off onto plan bouquets, is there anything that you would like to ask me now, or shall I proceed from here?
Yes, sir, I have some questions. Question number 1 is, what is the difference between hash join and merge join?
Okay, so these are different physical implementations of the same logical join operator. The logical join combines the information in 2 tables, like the student roll number and the roll number in the register table. Now, I don't want to go into the technical details of these two different algorithms because you need to, there's a lot of details there. So you can look that up in the standard database textbooks. Like there's a book by Koth, Silberschatz, and Sudarshan. Sudarshan is from IIT Bombay, which is gives you these details. But essentially, these are two ways of implementing the same objective. So think of it, I'll give you the analogy with sorting. You can do sorting of an array using either quick sort or bubble sort or selection sort or some other sorting mechanism. So, but the underlying objective is the logical operation is sorting. So in a similar way for join, we have about at least half a dozen different ways through which a database engine can implement the join. And one of them is hash join and another is sort merge join, which are very popular in the industry also. But you can look up the details in the textbook. Otherwise, if you have difficulty, you can send me an email later and I'll give you the appropriate pointers for them. But the analogy, as I said, is like with sorting, you have half a dozen different sorting algorithms, which you would have covered in your courses. These all are different implementations of the same logical sorting idea.
Okay. Second question is, what is query optimization?
Yeah, so as I said, in databases, one of the reasons that they're so popular is that you can give queries in the form of SQL, and SQL is not an imperative programming language, but a declarative programming language where you only specify the target without specifying the means to achieve the target. So query optimization is the process by which, given the objective that you have given, how does the database system figure out the ideal or most efficient strategy to reach that particular goal? So that is the optimization process. Saying you have said you want X, I have to somehow achieve that X. What is the best way to achieve X? That is the optimization process.
And where this relational algebra is exactly used in database practically?
Oh, actually, relational algebra is the complete core foundation of all database systems. And one of the places that this relational algebra, like the select, project, joins, unions, all these operators are used, is that in query rewriting. So, for example, as I said, you could have written the query as student join register and then join with course. But an alternative equivalent would be to join the course with register first and then with student. As I told you, the output is identical, but the running times could be different. But the reason that you know that the output is identical is because you can prove the properties of the relational algebra, that join is both commutative as well as an associative operator. So at the heart of all database engines, there's relational algebra as a core. In fact, it's not just the relational algebra that you saw in the textbook. There's a lot of extensions to it to include things which are related to second order logic. So for example, you have this like operator in SQL, which is essentially using wildcards. So you have this clean star operator, like saying like Sachin star, which allows you to find out all people whose name starts with Sachin. So that is comes under second order logic. So most database systems actually have also operators for not only the core first order logic, but also second order logic, also things like aggregations and functions and so on. Okay. But at the heart of the system is still the good old relational algebra. And in SQL, there is a combination of relational algebra and relational calculus. Whereas if you look at other languages like Quell, Quel, which was originally being supported by the Ingress database system, those are purely based on relational calculus.
What are the TPC benchmark databases which are used for performing most of the experiments in a paper published by you?
Oh, that's a very good question. So obviously here is somebody who's been doing experimental studies. Yeah, so TPC is what is called as the Transaction Processing Council. It's an independent industry watchdog group, which essentially takes all the well-known database engines in the world and does performance evaluation on them, and then it produces the results. So it is not affiliated with any specific company, because obviously then there will be an incentive to modulate the numbers to suit that company. This is an independent watchdog, as I said, and they produce these numbers every 3 months or so. So they have come up with these benchmarks for both transaction processing, which I have not talked about much here, as well as what are called as decision support queries or OLAP queries, where you give these complex queries that combine information in many tables and produce the answers from that, like the example that I showed you earlier. So there are several benchmarks which start with the prefix called TPC. So there's TPC-C, which is for transaction processing. But then for decision support queries, there's TPC-D, which was in the early mid-90s. And then there was a successor to our TPC-D, which was called TPC-H. And then subsequently, there is a newer version now, which is from about the last decade or so, called TPC-DS. The DS stands for decision support. This decision support benchmark has 99 different queries, all of which are on top of a large, essentially manufacturing database. And there are large fact tables and many smaller dimension tables there. And there are complex queries that are doing joins between many of these tables along with nesting and so on. So we typically use the TPC-DS benchmark in most of our recent papers. In the papers of until around 2010 or so, we were using the TPC-H benchmark. Subsequently, it was replaced by TPC-DS. That's what we're using. But today you'll find that there are other alternative benchmarks available as well. There is one based on IMD. So TPC-DS is a synthetic benchmark where all the data is fake. But there are real world benchmarks like the job benchmark, which is called the join order benchmark, which came out of Germany. And that is based on the IMDb database, which many of you will be familiar with, which captures information on movies, TV serials, and all the entertainment industry and so on. So there are alternative benchmarks as well. So we do usually on both the job as well as the TPC-DS benchmark.
Okay. Thank you, sir. I have received many more questions, so I will ask after this session.
Okay, sure. Okay, so I'll now move on to this new idea, as I said, of robust query processing called plan bouquets. The problem framework here, which I'll just quickly go through. And again, don't worry if you don't understand all the details. I'll give you a list of references that you can look at on our website. The big picture is what is important here. So firstly, what we will do is that we'll take this notion of cardinality, which is measured in number of rows, and convert it into a normalized value called a selectivity. And what is selectivity? It goes from 0 to 100%. And all that it's doing is to take the ratio of the estimated output rows to the maximum possible and multiply by 100. So for example, if you had a predicate in the SQL query, which said that I only want those courses which are the cheap courses, that is their fees is less than 1,000 rupees, then in the operator that you see to the right, which is called as the filter scan, because it's filtering out these courses, let's say that there are 20,000 courses that are available, out of which 4,000, that's 4 into 10 power 3 courses are cheap. Then what we would say is, out of the 20,000 courses, 4,000 are cheap, so the selectivity is 20%. So now on the right-hand side, you'll see an SQL query which says select star. Star means all the attributes from this combination of 3 tables, student, course, and register, which you already saw. It has the roll number join, it has the course number join, and it's also saying that I want to look at those courses which are cheap. So you want to look at the students who are registered for cheap courses. Okay? So this could be something that the government would be interested in. So given this particular query, you can now come up with a 3-dimensional space where each dimension refers to a particular operator's estimation. So for example, if you look at the x-axis, you see a sigma symbol there. Sigma is a symbol for looking at all the courses whose fees is less than 1,000. So the cell refers to the selectivity. So what this is telling you is, what is the expected selectivity going from 0 to 100% of the filter predicate line that all the courses that you're interested in are the cheap courses whose cost is less than 1,000. That's the x-axis. If you look at the y-axis, it's looking at the output selectivity of the join of the course and the register table, which is saying that how many students are registered for which courses. So that's the y-axis. And then the z-axis gives you the student with register join, and again the selectivity there. So you had 3 predicates in your original query. One was a filter predicate to remove certain courses which are not cheap, and the other 2 are the join predicates which combine the information across the tables. Each of them gives you a dimension, and each of them gives you a selectivity. So now on top of this, we could have these performance metrics that you see listed at the left. Firstly, the Q sub E tells you the estimated selectivity location in SS. SS is the selectivity space that I showed you, the 3-dimensional space. And Q sub E tells you the estimated location that the database system thinks the query is located here. So if you look at the picture on the right, you will see a red dot where it says that, oh, the database system, based on its internal estimations, thought the query was located at 5%, 2%, and 8% in this 3-dimensional space. then Q sub A is the actual location that you discover at runtime in the selectivity space. And that is the green bullet that you see towards the right top corner of the space. And now you can see that the actual location is very far from the estimated location. It's 75%, 62%, and 85%. Now, at the estimated location, there was an optimal strategy. We'll call that as P sub OE. So P stands for plan, O is optimal, and E is the estimated location. And similarly, there's an ideal plan strategy at the optimal location. There's an ideal plan strategy at the actual location, at Q sub A. So now what is going to happen is, because the database system thought that the query was located at Q sub E, let's say at the red point, and use the ideal plan there, at the actual location, which is Q sub A at the green dot. So you're using the red plans, the red points optimal strategy at the green dot. You are going to involve some sub-optimality because you're using a second rate choice. So the sub-optimality is the cost of running the optimal red plan at the green location, which is what you see in that simple equation that you see here, which is sub-optimality is the cost of the red plan at the green location normalized to the cost of the ideal green plan at the green location. And notice that this number can obviously only be 1 or larger than that and can be arbitrarily large. So this was for a specific pair of locations, estimated location and actual locations. What we want to look at is the worst case, that is across all pairs of locations. There's all pairs of estimated locations and actual locations. What is the maximum sub-optimality that you get? That is, what is your nightmare situation where you thought something and it turned out to be very different, and because of this, your query ran very, very slowly. That's what we are looking at here. So in order to solve this problem, we'll only make a small assumption, which is called as, and which is fairly mild and usually followed by all databases in practice. This is called as plan cost monotonicity. And the basic idea here is that if you take a specific execution plan P and two different locations in the space, let's say Q1 and Q2, what we can easily show is that the cost of executing this plan P at the location Q1 will be less than the cost of executing the same plan at the location Q2 if Q sub 1 is dominated by Q2. So that is the domination symbol that I'm showing before, because this is in multi-dimensional space. So just to put it very simply, what we are saying is that spatial domination implies cost domination. And this is shown to you pictorially in the right half of the slide, where you see this location called Q2, which is the green location at the end of the queue. And let us say that the cost of some plan P at this green location, Q sub 2, is 100. Then what we are saying is, within the cube, starting at the origin and ending at this Q sub 2, which is that box that the dotted box that you see, the cost of this plan at any location within this cube will be less than 100. Okay. Now, actually, this need not always be true, although it might be surprising. There are operators specifically like negation and so on, and existential operators, which need not always be true. But in most database queries, this would hold. So we'll assume that this is the case in the rest of the presentation. Okay, now let's look at how do contemporary database systems behave, and we'll just look at for simplicity, at a one-dimensional selectivity space. Okay, so we're looking at what happens given the selectivity going from 0 to 100% on a particular predicate, and we'll assume that there's only one such predicate. How do the existing database systems behave? So for this, we will assume that you are able to look at a parametric version of this query, which is what you see on the left-hand side of this slide, where we are saying that we will make the selectivity of the course table to be a parameterized value. So the earlier you saw in a specific example where you said course.fee should be less than 1,000 rupees. Assume that you can keep changing that value. So you say course.fee is less than 1,000 or less than 2,000 or less than 3,000, less than 4,000 and so on. Each time you change the value, the selectivity will change. So by changing the selectivity, by changing that value, you can change the value, the selectivity value from 0 to 100%. So that is by changing the fees bound from, let's say, 100 rupees all the way to 1 lakh rupees, you can change the selectivity of the course table from 0 to 100%. So you can keep issuing such queries to the database system. And based on this, you'll see that there's a graph on the right-hand side. The graph on the right-hand side on the x-axis is the selectivity value, which is determined by the constraint that you put on the fees. So for example, if the fees was put as less than 100 rupees, then very few fees would qualify. So you get something close to the origin. Whereas if you put the fees to be less than, let's say, 1 crore, virtually all the courses would qualify. So that gives you the right-hand side, which is 100%. Now, so on the x-axis is the selectivity value. On the y-axis is the estimated cost of the optimal plan for each of these selectivities. That is what you see as the green line. The green line is a cost line, but actually it is composed of multiple different plans. So as you go along, we will see that this initial part of the green line is actually the query plan that you see, which is shown there, where C, R, and S stand for the course, register, and student tables. And now you actually see the plan as well. There's a nested loops join between course and register, followed by another nested loops join with the student table. After you cross around 0.20%, now the optimal plan is a different plan called P2. Here, again, the base tables are student, course, and register, but notice that one of the nested loop joins has been replaced by MJ. MJ stands for merge join, or the sort merge join. So the explanation for the symbols is given to you at the bottom left of the slide. So S, C, and R are the student, course, and register tables. NL is nested loop join, MJ is sort merge join, and HJ is the hash join. So then after P2, you will transition to P3. Now you will notice that one of the nested loop joins is replaced by hash join. Then P4 actually has both of them being hash joins. And then when you go to P5, you will see that the join order has changed. In P4, it was R join C first, then followed by S. In P5, it is R join S first, and then followed by C. So this is how we got the optimal profile. And it's important to realize that this graph has been plotted on a log scale. So you can see that the cost values really change a lot from close to the origin where it's around 6,000 to all the way around 6 million at the top. Okay, so this is what we have in today's database systems, and this set of plans P1, P2, P3, P4, and P5 are called the parametric optimal set of plans, or POSP, because based on changing the selectivity parameter, you get different optimal plans in different ranges of the selectivity. Okay. So now if you take each of these optimal plans, which are optimal in a specific region of the space, and extend that behavior over the entire space, you get the picture that you see in this slide. So for example, you see that the red plan P1 is initially very good, but after some time, after around 0.2% of selectivity, it becomes worse than the blue plan. And so blue takes over, and then the maroon plan takes over, then the light blue plan takes over, and then the green plan takes over, and so on. So now, what could happen in this particular environment is that the ideal case is this green line that we saw earlier, composed of these 5 different plans. This is the best that you could hope to get for any of the queries in this selectivity range. But in practice, what you might get is the red line that you see above this, which is the worst case behavior of the current database systems. How do you get this worst case behavior? So let's look at the right-hand side extreme, that is at selectivity 100%. That is, you thought very few of the courses would qualify. You gave a certain constraint and you said, oh, very few courses will be cheap. But surprisingly, what you find is that 99% of the courses turn out to be cheap. And therefore, you are using the plan which was good at the origin, that is the red plan P1, instead at the actual location, which is at 99%. So here, if you take the ratio of the red plan to the green plan here, you find that there's a sub-optimality of 20. That is, your query will run 20 times slower because you badly underestimated the number of rows that would come out of the course table. You can have the flip side where you have done a gross overestimation. That you see at the left-hand wall of this particular two-dimensional graph. So here, what you see is that you thought that a large, so the estimated location is at 80%. So you've assumed that most of the courses are cheap, but you actually find out that very few of them actually turn out to be cheap when you look at the data itself. So here, you're going to be using the plan P5, which is good at the 100% region, or you find that there's a huge sub-optimality of around 100. That is because of the you made, your response time for your query will be 100 times slower than what it ideally should have been. So this is the profile that you see. And at any intermediate point, if you take the ratio of the red line to the green line, it tells you the suboptimality. And in this particular case, you find that the worst case suboptimality is at the origin, where you get this suboptimality of 100. That's the widest gap between the red line and the green. Okay, so now let's look at what the plan bouquet, which is our new technique, does instead on exactly the same environment. So what we do is we start with this initial graph composed of these 5 different plans as we already saw. And now please look at step 1, which you see on the right side column of this slide. We draw these horizontal lines, which essentially represent cost steps with a ratio of r equal to 2. That is, essentially, it is a geometric progression. So if you look, so I'll show you the lines that are being drawn now. Because this is on a log scale, they are equidistant. So each line here is essentially representing a doubling of the cost. So the first line is at 12,000, then you go to 24,000, then you go to 48,000, 96,000, and so on. Okay? So each horizontal line is 2 times the previous line. You just draw these horizontal lines on the original graph. Okay? And as I said, because this is on a log scale, the gaps between the lines are essentially look equidistant. In the second step, you look at when these horizontal lines were drawn, they will cut the optimal profile at certain points. And those are the black boxes that you see along the line. And you look at what is the optimal plan at each of these intersection locations. And in this case, you see in this slide, there is P1 at 4 locations, then there's P2, and there's P3 and P5. So these 4 plans, P1, P2, P3, and P5 form your plan bouquet. Notice that P4 is missing because it occurs in the region between 2 of these steps. And I forgot to mention, these steps are called as ISO cost steps because they are horizontal lines. So IC that you see on the right-hand side of the graph, IC1, IC2, and so on, all the way up to IC7. IC refers to ISO cost. That is, this is a horizontal line which is representing a fixed cost. So the P1 through P, and so the P4 plan occurs between 2 ISO cost steps, therefore it does not figure in the plan bouquet. Okay, now let us see how we will execute the query using the plan bouquet idea. So firstly, as I said, we completely changed the framework. We will not do any estimation at all. So let us say the actual query is located at 5%. We don't know this. I'm just telling you this is the final outcome that we'll see. What we will do is that we'll say we'll not try to estimate this 5%. Instead, we will start at the very beginning. So you'll see a green star at the origin. We will start there, and then we will do what you see on the right-hand side of the slide, where we say we execute the plan P1, which is known to be optimal in this region, with a budget equal to the first ISO cost step. What was the budget? That was 12,000. So we'll execute this. Now, because of plan cost monotonicity, you can easily show that P1 will not complete the entire query within this budget of 12,000 units of time. So it will proceed to some extent, but then after this budget of time is over, it will not have completed. So what we will do is we will essentially terminate the execution. We'll do a Control C, and what we will do, we'll throw away all the partial results that had been accumulated so far. We start all over again. We'll again execute this P1, but now we will double the budget. So instead of giving you 10 minutes or 12 minutes of time, I'll now give you 24 minutes of time. So you execute P1 with, in this case, 24,000 units of time, and do it again. It will also not complete. So you terminate the execution prematurely and throw away the results. Similarly, you do that the third time now with 48,000 budget. You do it once more with 96,000 budget. None of this will complete. Now you'll switch to another plan, which is P2, because you know that that is optimal in the new region. Now the budget you give is more. It's 1.9 lakhs. That also won't complete. Only finally what will complete is this plan P3, because it is to the right of the actual location, which is at 5%. And this you can show that it will complete because of plan cost monotonicity assumption. So the plan P3 will complete. The budget you had given was 3.8 lakhs. It will actually complete with a little lesser budget, which is in this case, 3.4 lakhs. So this is the execution pattern. So now when you look at this, whenever I have explained this idea to even people in the industry and so on, their first reaction is, this is entirely stupid ideas. Okay? And the reason is that we are doing a lot of wasted effort at both the planning time in terms of reducing this entire cost profile, which shows you the ideal profile. And then to make it worse, at the runtime, you're repeatedly doing this trial and error mechanism. And if the query doesn't finish within its budgeted time, you have to terminate it prematurely, and then you have to throw away all the effort that you spent so far and start again. So on the surface, this looks like a pair of extremely stupid ideas, which comes back to the original thesis of this particular talk, saying that nobody in the right mind should have done either of these things. And as I said, whenever I explain this idea to even people, experts in the industry, the first reaction is, this is, what have you been drinking? Okay, that's essentially what they say. But then as I show you, and their usual expectation is that this is a recipe for disaster. But as I'll show you in the rest of this talk, in the small time left, this actually works surprisingly well, okay? Because there is a combination of two stupid ideas coming together. So let's look at actually how much was the effort invested by our approach. So if you look at the total cost that was incurred by the bouquet, the initial cost was 12,000, then 24,000 and so on. So if you look at the right-hand box, you see all the costs that you paid, which was 12, 24, 48, 96, then 1.2 lakhs, and then finally 3.4 lakhs. That totally adds up to 7.1 lakhs. So the total amount that you paid was 7.1 lakhs. The ideal would have been 3.4 lakhs. So the offline oracle would have known that the query is located at 5% and would have said, let's use plan P3. It would also have spent 3.4 lakhs to execute the query. So if you look at the sub-optimality, that is how much have I overpaid or overspent in terms of time, that is 7.1 divided by 3.4. If you have the data set, you would see that you can do some fairly obvious optimizations on this and bring down the 7.1 to 6.3, which means that the ratio is 1.8, which is less than 2. But you might say that, okay, that worked out reasonably well. It was less than 2 for this particular case. Does it happen for every other case as well? So in this particular picture, we have drawn the performance of the plan bouquet, not just for the 5% case, but from 0% to 100%. And that is the blue line that you see. So the green line is the ideal. The red line is what you see in current database systems, and blue is the line that you see from the plan bouquet technique. And you'll see that over the entire spectrum from selectivity of close to 0% all the way to 100%, the plan bouquet never becomes worse than 3.1. So the maximum suboptimality is in the center of the picture, which corresponds to something like around 1% selectivity. And you'll see this vertical dotted arrow. That's the maximum ratio between the blue line and the green line, and that is about 3.1. So for this particular query, no matter where you use the plan bouquet, where the query actually lies, you will find that our approach is far superior to the conventional database system approach in terms. But then you might say, okay, this was maybe true for this particular query and you had carefully picked this query. It's possible that for other queries, maybe the native or data optimizer of the database engine, which it currently has, may do much better than you. You have just carefully chosen this example because it suits your purposes. Okay. So what I'll show you in the next couple of slides is that that's actually not the case. We can show that this is, we can prove that this is always the situation. So essentially, and the Q1, Q2, Q3 are all the locations which you are doing the transitioning from lines with a sense of direction across them. So if the query was actually located at Q sub A, which is between Q sub K minus 1 and Q sub K, the ideal algorithm would just go and directly execute the query with the ideal plan, which is located at that particular location. Whereas what we have to do is to essentially climb the staircase. We are starting all is located, can directly jump to it, and it takes a certain cost for it. Whereas you have to painfully climb this staircase. You are climbing it as a geometric progression until you finally reach the correct location. Okay? So that's the kind of visual analogy that you can have. And if you do the analysis, you can see that the cost of the bouquet algorithm is the cost of all these intermediate steps. That is, you paid the cost of the IC1, that is ISO cost 1, then IC2, and so on. So that's the 12,000, 24,000, and so on in the example that you had, all the way to up to cost IC sub k, where IC sub k is the first ISO cost after the Q sub a location. This is what you have to pay. And let us assume that this is a generic geometric progression where the initial cost is A and the common ratio between the steps is R. Okay? So then you get this simple summation of a geometric series of A plus AR and so on, and the formula that you see, which is the A into R to the power of k minus 1 divided by R minus 1. This is the cost that is paid by our bouquet algorithm in terms of time. What would the ideal algorithm have done? The ideal algorithm already knows that this query is located between Q sub k minus 1 and Q sub k. It in fact knows the exact location, and therefore it would find the ideal plan for that location. So the minimum cost that this would have to pay is the cost of IC sub k minus 1, which is A into R to the power of k minus 2. That's the very minimum. So we are trying to take the most conservative case where we assume the worst behavior for us and the best behavior for the ideal algorithm. So now if you take this ratio of these two formulas, which is the sub-optimality of the bouquet, you can show that this is upper bounded by R squared over R minus 1, where again, as I said, R is the common ratio of the geometric progression that you use to cut the profile with these steps, the isocost steps. And then what you can do is you can do a very trivial optimization to find out that at R equal to 2 minimizes this expression. So this function of R squared over R minus 1 reaches its lowest value at R equal to 2. And for this, the maximum suboptimality is equal to 4. Now you might say, okay, 4 is there, but isn't it possible that maybe I could get 2 or 3 with a different plan bouquet algorithm? Actually, you can also show that that is not possible. We have a proof in the paper which shows that the best performance achievable by any deterministic algorithm is actually 4. So you cannot improve on the plan bouquet algorithm, but you can do it in the randomized domain. So those of you who are familiar with randomized algorithms, you can look up our paper. We have a section on how you can improve this from 4 to something of the order of between 2 and 3 based on the kinds of randomizations that could be included into this algorithm. Okay? So I won't spend time on this. If you are interested, you can discuss this with me later. So finally, I'll wind up with showing you the actual empirical performance. That was the theoretical performance. Here is the actual empirical performance on the PostgreSQL engine. And on the x-axis, you have many queries, which are not just one-dimensional versions of the predicates, but these are multi-dimensional things. So the first prefix that you see for each of the things on the x-axis, like 3D, 4D, 5D, tells you the dimensionality of the space, which is the selectivity space. And then somebody had already asked me this question about benchmarks. The H and the DS refer to the TPC-H and the TPC-DS benchmarks. And the Q5, Q7, 15, 96, and so on refer to the query number within the benchmark. So the TPC-H benchmark has 22 queries. The TPC-DS benchmark has 99 queries. So the number refers to the query in the benchmark. On the y-axis, you have the worst case behavior, which as we defined earlier was the maximum suboptimality. And notice that this is on a log scale. So in this picture, you find the native optimizer, that is PostgreSQL, has these skyscrapers, which is the red columns. So you find that often Postgres has a suboptimality between 1,000 and 10,000. That means the performance of the query is 1,000 times slower than what should have been done ideally. And in some of the cases, you'll see it even goes above 10 to the power of 6, which means that you are more than 1,000,000 times slower on this query. Whereas in comparison, if you look at the plan bouquet algorithm, which is the green columns, you find that certainly they'll be worse than the ideal, but they're not horribly worse. They are within a factor of around 10 to 20 compared to the ideal problem, and converted it into a mildly horrible problem instead. So there, I can also tell you, you can look up our papers. You'll see that even in the commercial systems, similar the first time the plan bouquet approach gives you worst case performance guarantees. And these performance guarantees are also robust to any changes in the data distribution. So in the normal database systems, they're very sensitive to how the data is distributed in the columns. For us, we don't care because we never do estimations. So the plan bouquet remains the same irrespective of changes in the data distribution. It's also easy to deploy. You can build this as a layer on top of the existing database engines. You can build it on top of Postgres, which we have done. You can build it on top of the Microsoft SQL Server or on Oracle or on DB2 and so on. And finally, from the industry perspective, it gives you a repeatability in execution strategy, which is very important for them, because for them, more than high performance, stability is important. And we can show that our strategy gives you a consistent behavior compared to the typical database engines. So to wind up, if you are more interested in any more details on this project, even if you did not understand everything here, that's because there's a lot of work that has gone on over the last decade on it, but hopefully I was able to give you some flavor of the method of approach and what we are trying to do here. The complete details are on our website, which is given here. And what you will see is that there is a project called Quest. And in this Quest website, so if you just search for Quest and Database Systems Lab at IISc, you will find this particular page. And you will see that the original paper was at the ACM SIGMOD conference in 2014, where he gave the bare bones ideas. Then there was a demonstration of this idea at VLDB 2014, where it won the best demo in the world award. Then there was a subsequent more detailed paper in the ACM Transactions on Database Systems in 2016, which apart from the concepts also gave a lot more details on the implementation. Then there was a follow-up work in the IEEE ICD conference in 2017, which received the best student paper award, again across the entire world. And then a detailed version of this paper came out in the IEEE Transactions on Knowledge and Data Engineering. And recently I've been giving tutorials on robust query processing. This is actually a 3-hour tutorial with about 200 slides. The first version was given last year in China in the ICD conference in 2019. And then I'll be giving the second version in the VLDB conference, which was supposed to be held in Japan, but because of the COVID situation, it's become a virtual conference in the end of August. Okay, so the overall takeaway of this entire presentation is the following, that we had this notion of SQL queries, and we would like to, which are declarative queries, and we would like to have optimal strategies to execute the declarative queries. But in this process, we were getting this terrible demon which was coming in the middle, saying, do you know the correct selectivities or the cardinalities for each of the operators in your plant tree? And what we did was to do take the Gandhigiri approach of offering some flowers in the form of these different plants to this demon. And because of this, we are now able to get near optimal performance. So that's the overall message that I had in this particular talk. So as I said, I tried to use this notion of robust query processing to explain why you should not just throw away silly ideas, because sometimes in combination, silly ideas can actually work very well. So you must be on the lookout for things that may on the surface or superficially appear absurd, but try to see whether they can be put together in innovative ways and actually come out looking surprisingly good. So with that, I'll end this presentation and I'll be happy to field any other questions that you might have.
Thank you so much, sir. Some of the questions are there. One is, what is spatial domination?
Yeah, spatial domination means that suppose an object is in, let's say, 3-dimensional space, latitude, longitude, and altitude, X, Y, Z. Then if there is a point which has its XYZ values to be larger than the XYZ values of another point. So on the X dimension, on the Y dimension, and Z dimension individually, you are having a larger value. Then that is called a spatial domination. Because if you are higher in X but lower in Y, then you cannot really compare the two. So this is what is called as incomparable points. But if I have a higher value on every possible dimension, then I dominate you. That is the meaning of spatial domination.
And what is denormalization?
Oh, this is referring to something that I didn't cover in this talk. So denormalization is with regard to database systems. normally, or typically you go through this normalization process, which most of you would have studied in undergrad courses, where you try to come up with some kind of normal form, which is either 3NF or BCNF and things like that. So that normalization process is meant to minimize the redundancy and to minimize the possibility of having errors in the data. But in this process, also what happens is that the performance can suffer because you make the tables very small. Subsequently, when you ask real-world queries, you may result in a situation where you have to combine information again, and the join operator is very expensive. So sometimes what people do is, in spite of having redundancy, they decide to keep the table in its original form and not normalize it into smaller pieces. And when you do this combination, it's called as denormalization. So the denormalization increases the storage, but improves the performance. That's the space-time trade-off that you're taking.
And what are the latest research areas in DBMS?
Oh, if you look at any of the conferences, you'll see there's a vast number spread in the areas. One thing which is extremely popular today is, of course, the graph databases, because many of the social networks, for example, like a Facebook and so on, can be represented as graphs. So how do you host graphs in a database system? Do you build, do you try to somehow force feed it into existing relational systems, or do you build a system from scratch and create a special engine for graphs? What are the different kinds of questions you can ask? Because it's not the typical SQL queries. You will ask like shortest path queries or neighborhood queries or reachability queries and so on. So graph databases is extremely popular in today's world. Something else which is gained a lot of attention is also how do you use machine learning techniques to improve database configuration. So most database systems come with about 100 different parameters that you are supposed to set. Most people don't set them, they just use the database system as is. But there is a lot of configurability that is available, but only people who are experts in the area know how to set them. So can you do this in an automated way? And people have used various kinds of machine learning techniques to be able to learn the optimal setting for this very large number of knobs that you have for both the database configuration as well as the operation.
Jayant, would you like to ask something? Please unmute yourself. Jayanti? Sir, I personally attended one lecture in Goa during ACM Compute.
Yes, right.
And the lecture was on some of the properties, like acid properties were discussed during that lecture.
That's right.
And
right.
I discussed that acid properties with many of my colleagues. The way you explained there.
Okay. We use the Bollywood analogy for that.
Yeah, just I would like to request you, sir, please, if you can explain with the same manner today, what are the acid properties using the same examples.
Okay, so basically what we, at least I try to do when I'm teaching the database course at IISc is that I have always felt that it's much easier to understand any of these concepts if you look at its analogy in a parallel world. So pretty much we try to explain everything using either Bollywood movies or cricket or in general some kind of sport. Because then, so at least that's my experience, and I myself think always in a parallel world. I don't like to think in the original computer science world. So and you already saw that example, for example, here where we said there's a VVS Lakshman, there's a Rahul Dravid and MS Dhoni kind of approaches to these database problems. We have used the same analogy for the notion of acid transactions, that is atomicity, consistency, isolation, and durability. So the example that we showed is in most of our Hindi movies, what you'll see is that usually you'll have some of the bad characters who are the kidnappers will come and kidnap the girl, who is usually called as Mona. And there's a good person called Kishan, who is, let's say, a software engineer. And these bad people, let's say called Ajit, has come and kidnapped Mona. And then they'll say that I would like you to pay a ransom in order to return Mona to you. So what we try to look at is that in this very common movie scene, especially in the last century, you can see the acid properties coming up there. For example, the atomicity is that if you have decided to pay the money for Mona, you want to give the ransom money to the kidnappers, the atomicity is that either you give the money to the kidnappers and they give you Mona, or nothing is done at all. So should not be the case that you lose both money and the Mona, okay, which then was the worst case situation. So that is what we see by atomicity. And then the consistency refers to whether this transaction is doing the right thing in terms of maintaining the database state. So for example, you could have a failure in this transaction where either you give a fake money to the kidnappers, or in return they give you the fake Mona, because you may not be able to see it very well. It's done at midnight, these kinds of transactions. So something could be fake in this. That refers to consistency. The isolation is that you would obviously not want the police to witness this transfer of ransom money being done, because technically it's an illegal process. So if you had asked the police for permission, they would of course have said no. And you want to make sure that they do not see this transaction occurring, because they would stop it as soon as they hear of it. So that is the isolation part, where you are not able to see any of the intermediate transactional activities. Is not visible to anybody else, even though it occurs over a period of time. So either the police see you with the money, or they see you with Mona, and you can always tell them, oh, look, the kidnappers were nice and they decided to release her and now I got her back. But they do not see this transfer occurring where you have given a quid pro quo, where you provide the money in return for Mona. And then the durability is that once you exchange the money with the kidnappers, it is still possible that when you're going home, they might come back and again shoot you while you're walking off the beach where you have done this exchange, which then means that the transition as the transfer has occurred, but there is no long-term benefits for you. So the durability is that you get to keep that Mona has returned to you, and that this remains persistently, and it is not that subsequently the kidnappers keep the money and also shoot you, in which case the entire effort was in vain. Okay? So this is just a very quick picture of how you could explain asset transactions by using contemporary examples. Okay? And this in many other contexts as well. For example, there's something called privacy preserving data mining, which is a very important field where you try to ensure that high-level models are correct without revealing the low-level atomic data. And I often show an example that comes from Nagpur, where you find that illiterate women have actually used a similar idea. So I'll just give you a quick idea of it. So there was a small village near Nagpur which was being terrorized by one of the dacoits. And then after the men did not do anything about it. They used to just say, oh, I hope something happens to the guy, but he's always terrorizing us. We're too afraid of him. The entire village, all the women in the village teamed up together and said, we have had enough of this. So the next time this dacoit came there, they actually caught hold of him and they basically killed him. Yeah, so now you would expect that there's, of course, there'll be a police investigation immediately afterwards. You would expect that even each of these women is asked by the police that did you commit the murder? They would say, of course, not me. I was not even in town on that day. I was somewhere else and so on. That is a normal reaction. But what these village women did was a very interesting idea. They actually told the police, all of us have committed the murder. So whoever they would ask, they would say, oh, I have committed the murder. Okay. And she would say, please take me into prison. I am the culprit. I am the murderer. Please put me into jail for my sin. Now, if all the 300 women in the village say it, obviously the police know that most of them are lying, because it's not possible that they all did it. Some of them were in the periphery and some actually did it. But everyone in the crowd is saying, I committed the murder. Please put me into prison. And therefore, there is no way for the police to know who actually did it. So essentially, you are being lost in the crowd. So in a crowd, nobody knows who you are. And the same idea is actually today being used by privacy preserving mining techniques, where they use the notion of anonymization, where you cannot differentiate one database record from the others, because you are having a crowd, and in the crowd, you are usually invisible. So at least, as I said, there are many real-world scenarios that you can use to explain complex technical concepts, and at least I tend to find this, and I tell my students that a prerequisite for the course is that they must see a lot of movies. So they love that for that reason. And whenever the director asks them why you're watching so many movies, they say that it's because the database course I didn't want to watch, but Jayant is forcing us to watch it.
Great, sir. Thank you so much, sir. We are really honored today to have you with us. And this is first talk as the ACM president we are fortunate enough that you have delivered this talk today. I'm thankful to you, sir. And I hope that the participants have enjoyed the session. And this is the letter of appreciation from our side, sir. I will mail you.
Thank you very much for hosting me and for your patient listening. It was a pleasure for me.
Thank you. Thank you so much, sir. Thank you so much.
Okay.
Participants, you will receive the certificate within 4 or 5 days time. So thank you so much for your patience listening. And we hope that we will be planning more similar talks in the month of July also. So thank you so much. Jayant sir, thank you so much. I'm personally feeling honored, sir. Thank you so much.
Okay, no, it's my pleasure. Thank you.
Thank you. Thank you, sir.